right, in this video we will solve the differential equation 5y prime minus 2x squared y equals to 0 about the ordinary point x equals to 0 using power series. So in this case, we're going to assume a series of the form, a solution of the form y equals n equals to 0 to infinity of c sub n x to the n. So in this case, we need to take as many derivatives on the series as required in the differential equation. In this case, only one derivative, that is y prime equals sigma n equals 1 to infinity, and differentiating x to the n using the general power rule, that'll be n c sub n x to the n minus 1. All right. So that means that if we take the second derivative, then the starting index would be 2. If we take the third derivative, the starting index would be 3, etc., etc. All right? And the reason to that is because the term containing the n to the 0 is just a constant for the series. If we take the first derivative, that constant zeroes out. So now the first term that survived the differentiation would be the one related to n equals to 1. So that's the reason we start the series at 1. All right. So let's substitute all of this into the series. Okay. So that'll be 5 times sigma n equals 1 to infinity of n c sub n x to the n minus 1 minus 2x squared sigma n equals 0 to infinity of c sub n x to the n. Let that be equal to 0. All right. Well, so in this case, well, let's introduce the 5, which is just a constant, and let's introduce the 2x squared into the series also, which is a constant and a variable. So for the first term, that'll give us sigma n equals 1 to infinity time of 5 n c sub n x to the n minus 1. All right. Minus sigma n equals 0 to infinity of 2x to rather c sub n x to the n plus 2. All right. Well, in this case, the n plus 2 power comes from adding the exponents because we're multiplying the same base. Okay. So now, our next goal is to combine the two series together. There are different strategies to do so. In some cases, we need to perform a complete shifting in the series, or in one of the series, or maybe in all of the series, depending on the complexity of the equation we're working on. A complete shifting consists um, of shifting the starting index by, say, subtracting a number. We need to do the opposite in the ends in the series. That is, if we subtract a number in the starting index, we need to add that same number, but in the side of the series. If we add a number in the starting index, we need to do the opposite, which is to subtract um, the same value in on the ends inside of the series. Okay, so um, another way to shift is the incomplete shifting, in which only under certain conditions we can do. And the incomplete shifting consists of only shifting the starting index, right, without changing anything in the series, in the rule. Okay, so in this case, well, we would need to ask ourselves how many units is n minus 1 away from n plus 2? Well, the reason why we want to do that is because we want to write the series in terms of the highest power of x that we see. And in this case, we can see that between n minus 1 and n plus 2, they are 3 units apart. All right. Okay, so what we would think naturally is well, to get that n minus 1 to be an n plus 2, I would need to add 3 units, okay? And then we'll add 3 units to the remaining n's in the series. That means we would need to subtract 3 units in the starting index. Although that seems legitimate, um, with how we perform on a complete shifting, well, we have a little problem. If we do this, then our series will start a starting index with a negative number, and that is not part of a power series. Keep in mind that a power series has a starting index that goes between 0 and infinitely many terms. We do not consider negative indices. All right. So that means that if we subtract these three, we would be going 2 units into the dark side of the power series, so to speak. And you don't want to do that. How do we stay away from the dark side? Well, so if 1 minus 3 equals -2, that is -2, that is 2 units into the dark side, then the solution to this is to expand two terms in this case, that is expand n equals 1 and 2, right? So let's go ahead and do that, all right? So um, for n equals to 1, that'll be 5 times 1 times c sub 1, x to the 1 minus 1 plus 5 times 2 times c sub 2, x to the 2 minus 1. And then, because we expanded the terms corresponding to n equals 1 and 2, now our series will start at n equals to 3 to infinity 5n. 5n. C sub n, x to the n minus 1 minus sigma n equals 0 to infinity of 2 c sub n x to the n plus 2. Okay? And let that be equal to 0. All right. So let me simplify this expansion over here. 5 times 1, which is 5, and then c sub 1, and then times x to the 1 minus 1, which is x to the 0, which is 1 times c sub 1, that's simply c sub 1, plus 10 c sub 2, x to the 2 minus 1, that's just x. Okay, so c sub 2, x, and then plus, at this point, we may go ahead and perform a complete shifting to the series. That is, subtract 3 to turn it into a 0 to have the same starting index with the second series. Okay, however, we're going to do the opposite, which is add those same 3 units into all of the n's in our series. Okay, so fixing this series, that's going to leave us with sigma n equals 0 to infinity of 5 times n plus 3, c sub n plus 3, x to the n 3 minus 1, is that equal to plus 2, minus sigma n equals 0 to infinity of 2 c sub n x to the n plus 2. All right. Now, do you see how after expanding n equals 1 and 2, we are not going to the dark side of the power series, to the dark side of the series? That is no negative starting indices. So, and also that fixes both the starting index and the powers of x, which now we are in a safe place to combine these two series. All right. So the next step is to, okay, 5 c sub 1 plus 10 c sub 2 x plus one single series, that is sigma n equals 0 to infinity. Oh, I'm going to put a bracket. And essentially, I'm going to factor the sigma symbol on the left, and I'm going to factor x to the n plus 2 on the right. That's going to leave us with 5 n plus 3 c sub n plus 3 minus 2 c sub n. Okay, and that times x to the n plus 2, and let that be equal to 0. All right, well, so the next step over here is to equate coefficients. All right, so essentially the right hand side of the differential equation is the same as saying 0 plus 0x plus 0x squared plus dot 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 infinitely many terms plus 0x to the n plus 2 plus dot 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 infinitely many terms. So equating coefficients, that's going to give us the following. So on the one hand, the constant term 5c sub 1 must be equal to the constant term on the right hand side. That is 5c sub 1 equals to 0. Next, On the second term, 10 c sub 2x, that is, the coefficient of x to the first power on the left must be equal to the coefficient of x to the first power on the right. That is 10 c sub 2x, equal to 0. Okay, and then here the coefficient of x to the n plus 2 on the left hand side must be equal to the coefficient of x to the n plus 2 on the right hand side, which is 0. That is 5 n plus 3 c sub n plus 3 minus 2 c sub n equal to 0. With this equation, we're going to obtain what we call the recurrence relation, right? So this is the equation or the relation that we're going to use to obtain the coefficient of the power series and obtain the solution to the differential equation. All right, so the rule here is to solve for the c that has the largest subscript. In this case, I'm going to solve for c sub 3. So I'm going to add 2 c sub n to both sides and then divide both sides by 5n plus 3, leaving us with c sub n plus 3 equals to 2 c sub n over 5 times n minus 3. N plus 3, I mean. All right. So this is our recurrence relation. Okay, you guys, everything we're doing in when we're solving a differential equation using power series is meaningless. We are not just doing operations, manipulating powers, expanding terms, equating coefficients, generating terms. So everything here is meaningful. All right. So because here the next part is usually or typically the most tedious part of the method of solution, which is the generation of the coefficients. And well, in many cases, we may need to generate like too many terms in order to see a pattern to generate the power series. However, let me show you a way to actually make that shorter. Okay, let's analyze this recurrence relation. So this relation is telling us that c sub n plus 3 depends on c sub n. All right. So that means each coefficient only depends on 3 indices earlier. All right. So these coefficients will split into 3 independent chains. What do I mean? Let me write those chains for you. Okay, so the change for C sub 0, okay, C sub 0, another change for C sub 1, and another change for C sub 2. These are the 3 independent chains. Okay, let me generate some terms for each of the chains, okay? That is, okay, C sub 0, if we add 3 to 0, that is going to be C sub 3. If we add 3 to 3, that's C sub 6, and then C sub 9, etc. C sub 1, that'll be add 3 to the subscript, rather. That'll be C sub 4, C sub 7, and C sub 10, comma, dot, dot, dot. All right? And what else? That'll be C sub 2 plus 3, that's C sub 5, and then C sub 8, and C sub 11. And of course, there will be infinitely many more. What am I doing here? With this, we're gonna find a way to make the work a lot quicker. So remember, from the equating of the coefficients, we got that 5 c sub 1 equals to 0, which means c sub 1 equals to 0. Same, 10 c sub 2 equals to 0 means c sub 2 equals to 0. All right? What does that tell us? This tells us that c sub 1 equals to 0. In other words, that c sub 1 and all of the terms in its independent chain of coefficients are all going to be equal to 0. All right. The fact that c sub 2 equals to 0, that tells us that in the third independent chain of coefficients, starting at c sub 2, That's going to be 0. All of them are going to be equal to 0. What does that mean? That you do not have to bother and compute all of these coefficients all the way from C sub 11 or C sub 12, because in some cases you may need that many. Instead, just just obtain the coefficients for the the terms on the change that survive the cancellation. That is, we're going to compute only the terms for n equals to 0, n equals to 3, n equals to 6, and n equals to 9. That's going to be more than enough in this case. All right, well, so compute, okay, for n equals to 0, n equals to 0, that's going to give us 2 times c sub 0, okay, c sub 0 plus 3, which is c3, okay, equals to 2 times c sub 0 divided by 5 times 0 plus 3, which is times 3, simply times 3. All right? Okay. For n equals to 3, that'll be c sub 3 plus 3, which is 6, equals to 2 c sub 3 divided by 5 times 3 plus 3, which is 6. And I know you want to divide 2 over 6, but no, do not divide that, right? Don't divide it. You'll see what's going to happen. Now, here is the thing. C3 should be written in terms of C sub 0, because we know what C sub 3 is, right? That we found that one in the previous computation. So this will be 2 over 5 times 6 times c sub 3, which is 2 over 5 times 3 times c sub 0, right? What is this equal to? This will be equal to 2 squared. Let me write it as a 2 squared. I know it's equal to 4, but leave it in terms of 2 squared. And then what about 5 times 5? Let me write that down as 5 squared. And then what do we have? 6 and 3. Okay, 6 and 3. All right. So this will be 6 times 3, C sub 0. All right. And let me compute one more. The one for C sub 6, maybe. N equals to 6. That is from the recurrence relation. C sub 6 plus 3, that'll be C sub 9. That equals 2 times C sub 6 in this case, divided by 5 times 6 plus 3, which is actually times 9. All right. But again, we need to write this C sub 6 in terms of C sub 0. So we know from the previous term, okay, that this is going to be 2 over 5 times 9 C sub, times whatever we got from before, that is 2 squared over 5 squared times 6 times 3 C sub 0. And simplifying, well, not all the way, that's going to give us 2 cubed, 2 cubed, okay, divided by 2 cubed divided by 5 times 2 squared, that's a 5 cubed, and then 6 times 9 times 6 times 3, right? 9 times 6 times 3. That's going to be C sub 0. I think this is good enough in terms of computing some of the coefficients. Now, the question here is, what does that represent? Okay, so the C sub 3, this will be, okay, the coefficient. Let me use a different color for this. Um, this will be, mhm, this will be the coefficient of x cubed. This will be the coefficient of x to the 6. And this will be the coefficient of x to the 9. All right? So remember what happened to the remaining terms? They were zeros, right? Okay, so here we go. We are ready to write our solution in terms of a power series, right? So that'll be y equals, I'm just going to write c sub 0 plus c sub 3 x cubed plus c sub 6 x to the 6 plus c sub 9 x to the 9 plus infinitely many terms. I know. Notice how I skip the one, the first term, the second, the fourth, the fifth, the seventh, the eighth, because again, those were zeros. And all we're going to do is related to the computations. We just do it over here. Okay, so substituting everything in terms of c sub 0, okay, this will be y equals to c sub 0 plus 2 over 5 times 3 c sub 0 x cubed plus c sub 6, which is 2 squared over 5 squared times 6 times 3 c sub 0 x to the 6 plus c sub 9, which is 2 to the third power over 5 cubed times 9 times 3 times 6 c sub 0, okay, c sub 0 x to the ninth power. And of course, there's infinitely many terms in the series. All right. So now let's write this using a power using a power series actually in sigma notation. And although we already have some sort of a pattern here, because we can see the power of 2 that goes to the first power, to the second, to the third, to the 0 power for c sub 0, etc. We also have the powers of 5, but we also sort of see, check this out, that you see the power of x, which is 9, coincident with the 9 multiplying here, the power of 6 multiplying, having a the power of 6 coinciding with the factor of 6 over here, the power of 3 coinciding with the factor of 3. So in a way, that's like a factorial or so, but it's not quite a factorial because we do not have all of the integers below 9, so we can write a factorial. So what I'm going to do here is I'm going to rewrite the terms of the series here, actually just the denominator. So okay, so that'll be equal to y equals to c sub 0, okay, plus 2 divided by 5 times 3 c sub 0 x cubed plus 2 cubed, 2 squared rather, divided by 5, 5 times 5 squared. Okay, what about this 6 times 3? Do you agree, hopefully, that this 6 is the same as saying 3 times 2, right? And well, this 3 with this 3 makes it um, a 3 squared, okay? And that's going to leave it with the 2 times an invisible 1 over here. So that is 2 times 1, all right? And that's going to be c sub 0 x to the 6, all right? And then plus. Okay, let's analyze the denominator in the previous expansion. This 9 is the same as saying 3 times 3. Can we use a different color for this? Okay, 3 times 3. I should have written this as a 6 times 3, not a 3 times 6. 6, 3, okay. Make some space. This will be then 6 times 2, and this is not 6 times 2, 3 times 2, and this is 3 times 1, right? 3 times 1. So what is this going to do? 3 times 3 times 3, isn't that going to be 3 cubed? Okay, so let me go back to the color. So that'll be a 2 cubed divided by 5 cubed. That is 3 times 3 times 3, that's 3 cubed. And then that's going to leave us with 3 times 2 times 1. 3 times 2 times 1, c sub 0, x to the 9. All right. Now, what do we have? Do you see the pattern? Well, so this will be y equals to c sub 0. I'm going to factor out the c sub 0, and I'm ready to write the series in sigma notation. N equals 0 to infinity of, notice we have powers of 2, that is 2 to the n divided by 5 to the n times 3 to the n, and then uh, 3 times 2 times 1, 2 times 1, that's actually our n factorial. And well, in this case, x to the, notice that for every n, see how the power is 3 times the the factorial we're evaluating here. So 2 times 3 equals to 6, 3 times 3 equals to 9. So that's x to the 3n, right? And that is our series in sigma notation, right? Okay, so that's final answer. Now, we may need to go the extra mile, and we will, and write the elementary function that is related, that is represented by this series here. Well, so again, that shouldn't scare you because all we do is identify the factor that stands out the most in a power series. In this case, it's usually the factorial. If you see an n plus 1 factorial, it's going to be the exponential function. If you see a 2n factorial and also an alternating series, that's a cosine function. If you see, say, a 2n plus 1 factorial also with an alternating series, that should be, or that most likely should take us to a sine function. All right, so in this case, well, let me show you a summary of this power series. Well, in this case, series number one over here, the one with the n factorial, but somehow we need to generate a composition function composed by some u to the n power. That should be the hardest problem in the world. All right, let's go about it. All right, so I'm going to write y equals to c sub 0 uh, sigma n equals 1 to infinity of, notice I can write everything to the n power here. The 2, the 5, the 3, and the x cubed. That'll be simply 2 over 5 times 3 times x cubed, everything to the n power divided by n factorial, right? This will be equal to, sigma, c sub 0 rather, sigma n equals 0, not 1, n equals 0 to infinity, 2 over 5 times 3, that equals 2 over 15 x cubed to the n over n factorial. Um, and y equals to c sub 0, sigma n equals 0 to infinity of u to the n over n factorial, where in this case u will be 2 over 15 x cubed. And well, this sigma series is equivalent to saying simply c e to the u, where u equals to 2 over 15 over x cubed. All right? I mean, 2 over 15 times x cubed. And substituting into the u, that'll be c e to the u, e to the 2x cubed over 15. So that'll be our final answer in elementary function and in sigma notation. Again, not in all it is not always possible to, number one, obtain the sigma notation the way we did it for this example. And even if it were, uh, we may or may not be able to express our solution into an elementary function.